Hello, everybody. I am Dr. Shobha, professor at RV College of Engineering, Bengaluru, India. Today, I am here to present to you the contributions that we have made to HPCC systems from virtual collaborations to virtual reality. So these contributions were made by RVCE team. So in this session, I am happy to introduce the academic collaborations that we had with LexisNexis Risk Solutions. I'll be sharing with you the projects and the internship executed during our long 4 years journey. The agenda follows like this. These are all the projects that we have executed. We have developed IoT Plugin for HPCC systems, data skew profiling, Octave Plugin, image processing plugin, machine learning evaluation metrics, parallel DB-scan algorithm, adaptive DB-scan algorithm, generative adversarial network, and some case studies which include COVID-19 data tracker and recommendation system in virtual reality environment. So to begin with, we have IoT plugin for HPCC systems. So as we all are aware that HPCC systems are useful for end-to-end big data solutions. So big data being used in IoT applications, which makes use of sensors to gather the data, to analyze the data and to extract the meaningful information from the sensors is a very important task in big data. But the IoT application currently is not supported by HPCC systems. So this motivated us to work on the project IoT plugin for HPCC systems. So we have used an IoT, that is industrial protocol, that is MQTT. So MQTT, what it does is, it is going to collect the data. For example, if we want to know the working of MQTT, you have a temperature sensor. So it collects the data from the temperature, and MQTT broker organizes the data from the temperature and publishes it to the devices that has been subscribed to the MQTT broker in a particular topic. So this concept is used for all IoT applications. So the same was taken for the proposed system design. So you can see here we have different sensors: temperature sensor, motion sensor, moisture sensor, and we have an MQTT broker which collects all the information. And based upon what applications that particular data has been used, it organizes the data based on the particular topic. But MQTT broker is a stateful protocol. But in HPCC system, we have a ROXY, which is stateless. So there is a mismatch in the protocol. So in order to correct this particular mismatch, we have a client, that is a middleware client, which collects the data from MQTT broker, organizes that into the queue. Then we have a queue thing which collects the data from the queue and then publishes it to the Kafka cluster by invoking HTTP request. Once the HTTP request has provoked in Kafka cluster, for every X minutes, the data will be sprayed into the HPCC cluster. Further, the data from the cluster can be analyzed, and we can make use of machine learning algorithms for analyzing. So we can see the outcome of the Kafka, that is message received at Kafka in WS ECL Watch. As you can see, this is the screenshot we have taken. It represents the partition, the offset, and the exact message that has been received. We also get the message count and the last message offset and what partition count. So here in the particular example, we have taken only one partition, that is partition 0. The same thing can be recaptured by ECL Watch. So ECL Watch also shows what are all the partitions you have in the data, its offset, and plus the relative messages. So this is the outcome of this IoT plugin. We have tested with a small toy, wherein the speed, as and when the speed of the car increases, the intensity of the light also increases. So we have here vehicle ID, timestamp, all those stuffs. So this data will be sprayed into the HPCC cluster, and we can make use of the machine learning algorithms that are present currently in the HPCC bundle for further analyzing. This is about IoT plugin for HPCC system. Okay, going forward, we have one more contribution, that is data skew profiling. So as the data is sprayed in the HPCC cluster, there will be a skew. So it is necessary to analyze the impact of differently skewed data distribution on the most commonly used operations, such as normalize, denormalize, join, sort, table, project, and to know the runtime for the operations that will be frequently using. So we have the skew distribution like 0, 20, 40, 50, like this, varying skew distribution, and varying data will be used here. And the operations such as the normalize or denormalize will be applied to this particular skew. This will help the developers to use the operation depending upon their application and the skew distribution. For example, if you take a normalize operations, you can see that the runtime is very less when the skew is lower. But whereas in the denormalize, it is more. Runtime is more when the skew distribution is less. So that means what? The normalize, as we know, the functionality, it takes a record set and it adds all the child record to the parent. So, but whereas in the denormalize, it takes a parent record set and the child record set, and it combinedly add parent to the child. If the parent and child are in one particular node, then it is very easy. The runtime will be less. But when it is distributed through a number of nodes, definitely it will take more runtime. Okay, but we have tried for various distributions and various data set, and we have tabulated the result here. Similarly, we have join, sort, table, and project. So this tabulation helps the developers to use the frequently used operation as mentioned here, depending upon his application. And coming forward, we have also contributed an Octave plugin for HPCC systems. So Octave, as we are already aware, it is an open source programming language, and it is basically used for complex numerical operations. Since that facility was not there in HPCC systems, we provided a plugin for the HPCC systems. As we know that the ECL supports the external language, so all the syntax and all the other semantic structures of Octave will be defined in .ecl lib and will be submitted to the engine, which consists of Thor and Roxy. If there is a sample ECL code which contains Octave function and that is submitted to the engine, based upon what functionality the sample ECL has, that functionality will be activated in the octave.ec lib, and depending upon that, the following compile embedded script, bind, call function, and get function will be executed to provide the output of the numerical calculation. So this is about Octave plugin. And coming forward, we have also developed the image processing plugin for HPCC systems. We have contributed, in fact. So this image processing, we had taken it from the OpenCV. The ECL language was provided an interface to take the functionality of the OpenCV libraries. And we used one simple image processing algorithm that is basically to try out with license plate detection. This license plate detection made use of image processing libraries such as the edge detection, segmentation, character recognition, etc. So this processing was called from the ECL interface, and then based upon the libraries, the functionality was executed. And you can see the results here. Okay, we have varying sizes, varying images, like we have 25,000, 50,000, and so on. And the time for the image processing was also computed. Okay, so this was found to be satisfactory. Next, coming to the machine learning evaluation matrices on HPCC systems. Here, what we did is we summarized all the machine learning evaluation metrics that was currently available in the library, and found that this machine learning matrices, that is balanced F4, Hamming loss, silhouetted coefficient, chi-square, adjusted random index, area under ROC was not there. So we have contributed this and also tested the same in Python scikit library. Okay, here the result we are tabulating, that is silhouette coefficient. Okay, what we did is we tested whatever we have implemented, we tested on the scikit, Python scikit, and we got the same result that was compared with the ML core library that we had contributed with the HPCC. So the results were promising. And to be just to share with you, these are all are in production. Next is one case study, that is ML techniques to detect the fraud in credit cards. So in this case study, we have taken the machine learning algorithms from the HPCC, that is random forest, learning trees, LSTM, and convolution neural network. But getting the data was again a challenging, because whatever data we get is an imbalanced data. So we took European credit card transaction, wherein we had somewhere around 4 lakhs, out of which only 500 records were found to be fraud. So there was an imbalance in the data. So we corrected that imbalance by making use of the window sequence size 4, that is conversion of each sample into the window size, where we have kept it as a constant 4. Then we reconstructed the data set by oversampling it so that the imbalance is not achieved here. After that, after pre-processing, we divided the data into training set and testing set. After training, okay, we tested the results and we found that learning trees and CNN was better, which provided an accuracy of 0.9968 and CNN provided 0.6887 compared to LSTM, which had only 0.973. Okay, and we also compared the performance with HPCC system and without HPCC systems, and we found that the drastical down time in case of HPCC system, which took only 37 minutes and 20 seconds, but whereas without HP system, it took more than 1 hour. This is about the fraud detection in credit card. Next, coming to density-based clustering algorithm. Here, we have made use of density-based spatial clustering algorithm, mainly to overcome the noise. This clustering algorithm has 2 input parameters, that is an epsilon and the minimum points. Epsilon is nothing but the radius, the maximum radius of the neighborhood, and minimum point is nothing but the number of data points within that epsilon, how many should be there, the user should specify. And we also have one more thing to look into, that is nearest point to a particular data point, say P. Nearest point, nearest neighborhood for a point P. Okay, if I say Q, then Q should belong to the data set, and the distance of P and Q should be less than or equal to epsilon. Then from that particular point P, we have to see which are all the points that are directly reachable. If a point Q is directly reachable, then it should obey these 2 points. P should belong to the nearest neighborhood of Q, and the core point condition is nearest neighborhood of Q, okay, should be greater than or equal to minimum number of points. So this is the dbScan algorithm, which is already available iteratively. Now, what we have done, what we have contributed to HPCC system is, we have developed a parallel dbScan algorithm. So in this parallel dbScan algorithm, we decompose the clustering algorithm into 3 parts. One is spraying of data and local clustering and global merge. So after attaining this, we compared the results with varying data sizes, like 4,800 to 50,000, with varying radius and varying minimum points. And also we tabulated the time taken for single node, 2 nodes, and 3 nodes. As you can see here, there is a drastic difference in the time. As and when the data increases, you have the time taken for 3 nodes is that 3,266, whereas with a single node is 24,948 in seconds. Okay, So this was again a contribution, and it is in the production side. The next one is that we're taking the drawback of DB scan. That is, as we saw in the previous slide, it should have an epsilon and also the minimum number of points. Even though the data is varying, this will be a fixed thing. So in order to avoid this, we also proposed an adaptive DB scan algorithm. So in adaptive DB scan algorithm, we made use of grid search, which is going to identify the threshold density, that is the minimum density of the particular data set, and also the minimum points. Again, it depends upon the size of the data. That is, minimum point is equal to 0.1 into data size. So this was an adaptive DB scan, and and this is the proposed method which overcomes the DB scan algorithm. So going forward, we looked into the application of the generalized neural network that is found in HPCC machine learning bundle. So it can be used for various applications, but this generative adversarial network was not available in the GNN. So attempt was made to contribute this GAN to HPCC machine learning bundle. So GAN, as the name itself suggests, generalized neural network. From the figure, you can just look into, we have a real world images, and whatever sample we are deriving from the real world images or the real images, but what we are also going to generate the sample. That sample may be fake. So there is a discriminator which checks the sample and determines how exactly it is not matching with the real. That is nothing but a loss. Then this loss can be minimized by back propagating the error and updating the discriminator weights. Okay, so an attempt was made to develop generator and discriminator networks. Okay, and training was provided in batches, and it made use of weight transfer technology so that generator and discriminator works advisory. Okay, this was the GAN that we contributed to the bundle. So we also got the result by making use of simple GAN, and also we made use of deep convolution neural network. Okay, and we found that the promising results was found with whatever we have implemented in HPCC bundle. So this is about the GAN. And going forward, we have one more case study, that is COVID-19 cases and vaccination data tracker, that is in India. So data is visualized by using the visualizer from ECL bundle. So here the state-wise COVID cases data was tracked here. Okay, then the static numbers we got, and the vaccination trend in the country, and also state-wise total vaccination done till date was also tabulated. That means we have used the visualizer of the ECL bundle to get the statistics of COVID-19 cases. This was one more case study. And going forward, we have one more project, that is recommendation system in the virtual reality environment. In this, we have made use of a Unity software wherein we developed a VR application. That means we simulated a storeroom, okay, which gave a 360-degree view of the showroom, in which the user can experience by buying the product from in the 3D view. It had 4 components. One is the VR application, front end, and external database, and the recommendation engine. So as I told you, VR application, we made use of Unity. When front end application, wherein the user used it for buying the products, and these products were in the 3D view. And we had used SQL and NoSQL databases. SQL databases to keep track of the inventory, to keep track of the billing information, products, etc. And the NoSQL for the reviews of each of the products. And for this, we developed a recommendation engine. Okay, the recommendation system for the VR is built by making use of the purchase history, not only the data, but also the user behavioral data. It uses neural network-based collaborative filtering model to generate the list of recommendation. And this list appeared in the panel in the virtual environment for the user. So we had made use of a open source database, that is, the link is given here, and we trained it and comparison was made on GPU and also with HPCC system and Spark on Hadoop. So as you can see from the graph, GPU took huge amount of time, okay? But whereas the distributed platform, HPCC and Spark on Hadoop, as it is distributed, it takes less amount of time. Even though Spark on Hadoop is faster in training, the results feature of HPCC as a better platform for real-time interfacing was found in the HPCC Systems Platform. Okay, this was the recommendation system in the virtual reality. So this is about my presentation, that is from the virtual collaboration to the virtual reality. To summarize this, we have successfully completed 4 years of collaboration with LexisNexis solutions, and 13 projects were completed successfully under the supervision of HPCC Systems Mentor. Parallel DB scan and ML evaluation metrics, whatever we have developed or in production, and of course, under the supervision of the mentors from LexisNexis. We have also introduced an elective course on HPCC systems and published 10 papers in reputed journal and conference proceedings, conducted various workshops and FTCs to many colleges in India. Finally, I would like to thank LexisNexis solution team for supporting us in contributing towards HPCC systems. Thank you.